We've seen what happens if we eliminate z. We get a locus of points in the xy plane, and the intersection of the two surfaces lies above or below that locus of points. Now, there's no reason it had to be z that we eliminated, just because z happens to be easy to eliminate. We could also have eliminated x, and that's easy to do if we subtract 4 times the second equation from the first. I'm not going to do the arithmetic on paper here, but I believe, and you can verify, that this comes out 5y squared minus 5z squared equals negative 28. This would be a hyperbola, y squared over about 5.3 squared plus z squared over about 5.3 squared equals 1. And if we look in the yz plane, put z here, y here, we're going to have to draw it in a little smaller scale than before, but we come out 5.3 units here, same distance here, and turns out the same distance up here, same distance down here. Sketch our rectangle, sketch our diagonals. We determine that y can equal 0 if z equals 5.3, giving us points here and here. So we have a hyperbola in the yz plane that approaches its asymptotes starting from these two vertices. Now, what does that hyperbola look like if we go into a third dimension? This line might look like an x-axis, so let me put that idea to rest by drawing my x-axis in this direction. So I've got x, y, z. We're looking at this from a little different perspective than we did over here. But these hyperbolas are in the yz plane. If I draw an auxiliary set of axes at some other point that intersects the x-axis, I'm going to get a similar figure with parallel diagonals parallel to those that I had before, and they don't quite come out that way the way I've sketched it here. Vertices here and down here, and just taking this top vertex, we can come out and approach this asymptote. We can come over and approach this asymptote. I'm not doing that very well. And then we can sketch line segments actually parallel to the x-axis, which is like so. And we can see that this forms sort of a trough in three-dimensional space. We could bring this back to here and draw a similar figure so that we could extend this back here and get an idea of what the shape looks like. And this shape will intersect our sphere. Actually, this shape won't intersect our sphere because our sphere has radius only 6. And that might indicate that I've got some sort of an error in the sketching. In any case, if I've got my arithmetic right, this hyperbola should intersect the sphere on the same locus of points that this elliptical cylinder intersects our sphere, and that's the same locus of points in which either of these shapes intersects our hyperbolic, our elliptical hyperbola that corresponds to this set of points.